All right. We have 10 people in the stream. That's good. We have a question out there. 3 votes for people feeling okay about MOJ. That's what we talked about last time. So okay is good. It's not great apparently, but that's okay. We're going to continue talking about that method of joints. We're going to add on method of sections. Both of these are what would it be? Tools that you can use for planar trusses. So last time, if you didn't watch the previous video, you probably need to go watch that one and then this one, because we defined a lot of like what is a planar truss. We talked about how you calculate moments in general. Moments aren't specific to trusses, but we needed them, and we definitely need them today when we talk about method of sections. But the general idea from last time was that we had these structures called trusses. They had a couple of rules that were necessary, or assumptions that we had to make, like the trusses were rigid members connected together at pin joints. The joints were frictionless, and in the end, only forces, external forces, could only be applied at those joints, and every member therefore was what we called a two-force member. And then we could look at every individual joint of the truss and draw a concurrent force system. Since we were doing planar trusses, it was a 2D concurrent force system. And then we could solve for the unknown member forces for that particular joint, and then we could move to a different one and solve for those member forces. So that's what we did last time. Looks like now we've 7 votes, and they're all okay. So that's good. We do have, let's go to our web page here. So we do have quiz 1 is open. I think it's still open for a couple more days. I don't remember, but remember that's just a practice type quiz. It does count in your grade, but it's really set up for practice. Here we are today on method of sections. We are about to do one more topic on Wednesday, and then we will have just kind of a review of all the things that we've done from the beginning of the quarter to now. And then quiz 2 will open. We'll talk about some new topics. And then exam 1 will be on June 26th. So if you had looked at this previous, there was a date over here on the left-hand side and a date on the right-hand side, and they didn't match. They were 2 different dates. The one on the right-hand side is the correct one, so I just removed the one on the left-hand side. That must have been from last year. So June 26th, that's Wednesday, the 26th, will be exam 1. We'll talk more about how we're going to do exam 1 when it gets close, during the exam review. All right, so back to trusses and method of sections today. We'll probably do some method of joints also, just to refresh that, but the real topic is method of sections. So to do that, let's go over to, let me move something around here. There, maybe. There we go. So, where's my pen? We are talking about the method of, okay, I didn't need that, of sections. Last time, we talked about the method of joints. Both of these are only used for trusses. So the structures that we deal with these 2 methods have to follow all those assumptions from last time. So these are only for trusses. Whoops, can't spell. For trusses. And we're only going to use them on planar trusses, although you could use non-planar trusses too. But we're only going to do planar trusses. So last time, just to recap, method of joints meant that treat every joint as a concurrent force system. So we had, well, let's see, we did something like this. So there's one of them. That's what we did last time. This was joint A for our super simple little truss here that we drew. And it was this joint. We had already found the external reactions here. That's these red arrows. And then we went to joint A and made it a 2D, in this case, concurrent force system, and solved for the force in AB and the force in member AD. And we just did that using equilibrium equations. So that was method of joints. So it's good, particularly if you only have two unknowns, because you only can use two equations. Let's see, I wrote them down somewhere over here. Where did I write them? Well, they're down here. So you have summation of forces in X and summation of forces in Y. So you only have two equations. Now, if we were doing 3D trusses and there was a Z direction, we would have three equations. So we could solve for one more unknown, assuming that it had some Z component. So method of joints, only two unknowns at a joint. If there were more than two unknowns at that joint, we couldn't solve there. We couldn't start there. We'd have to work somewhere else and work our way over to it. It is typically good, method of joints, typically, good for the perimeter of the truss. So not necessarily the inside part of the truss, but for a joint on the perimeter. So like we used joint A here, which was over on the edge. Now this one only has a perimeter, so that, I guess we could have done any of them and they were on the perimeter. But typically it's good for that. Or if you're trying to solve for all the members on the whole truss. So if you just want everything, then you go joint by joint and you can solve for everything. Method of sections is, I guess, maybe more specialized. It's used if you only want a certain member and it's towards the inside of the truss somewhere. So method of sections treat the truss as two completely separate sections. We'll talk about that more in a minute. Treat the truss as two separate sections. There's the, method of sections. So you basically find somewhere you want to cut the truss apart and you cut it completely into two separate sections. Now, one little rule for that is that when you're making those two sections, when creating the sections, you can only cut through three pieces. And I'll put cut in parentheses. You don't, actually cut the thing apart. You just draw a free body diagram. So, why would you only cut through three pieces? It seems kind of arbitrary. The reason only three is because, just like method of joints, you had two unknowns, summation of forces in X equals 0 and in Y equals 0. And Z if you were doing 3D trusses, but we're only doing 2D. Here, since I don't have a concurrent force system, I've got a whole section of a truss. I have three equations, X, Y, and then that new thing that we did last time, summation of moments about some point. So that's why you can only cut through three members, is because you can only solve for three unknowns. So summation of forces in X equals 0, Y equals 0, Y equals 0, and summation of moments about some point equals 0. So there's your three equations you can write. You can solve for three unknowns. And so it's typically good if you're looking for a particular member or two, or three, I guess, that are kind of located towards the inside part of the truss. You can still use method of joints, but you might have to write several several joints before you get to the middle of the truss. Whereas with method of sections, you might be able to just go straight to the thing you want to solve for. So typically good for solving for members in the middle of the truss. Okay, so how do we do this? So I've got some pictures. Just these I pulled up because we've been talking about trusses with having joints, and we've been talking about these frictionless pins and all that. And so these are just some pictures I found various places on the internet that show a couple of ways that these truss joints might be really built. So here's typical, this one in the top left. Let me move this one down so we can refer to them easier. So top left, that's kind of what you normally see. There's no actual pin, but if you notice the members, they kind of all intersect at one point. So that point is kind of like this virtual pin that holds them all together. Because also remember, with our truss assumptions, we said that every member was a concurrent force. It had a concurrent force in it. Well, it was a two-force member, and it created a concurrent force system. Over here, this one kind of goes off the page, but you can kind of see these would all intersect somewhere over here, but there's no pin. There's a whole bunch of little rivets everywhere holding these things together. But sometimes, they do have actual pins. Not as common, but sometimes there might be a hinge somewhere, or they did build it with actual pins in place versus riveting individual members together to these gusset plates. So that's kind of the idea of this joint thing. We don't have to have an actual pin. We're just going to treat the joint like it's a pin, whether it's a real pin or whether it's one of these gusset plates with a whole bunch of members riveted or bolted to it or even welded to it. We're going to treat that like a frictionless pin. All right, so I went and got us 2 trusses here that we can work on. Nothing special about these trusses. They're just ones I found on the internet. Why don't we analyze the one on the right? It's got more stuff going on. So I've got to try and determine some of the stuff's in the background, so it's kind of hard to tell what is what. I'm looking at, okay, I think I see. All right, so let me outline the actual truss. So this is actually 2 parallel trusses, 2 planar parallel trusses, connected together with all these spars and this road bed and all this kind of stuff that's holding it together. But here's the actual truss. So there's, whoops, didn't want to do that. These are our members. Now, this member here, oh, that didn't show up very well, did it? This member is, in the real world, that's one long piece, but remember, we have to treat them as 2 separate pieces because there's another member in between there. So there's a joint right there. And so we have to treat that as 2 separate members, even though in the real world it's built like one big piece. There's one, there's one, there's one. Oh, again, that's 2 separate ones. All of this bottom is individual pieces. Same thing with the top. Even though in the real world it's one long piece, we treat it as individual pieces. All right, now that's all like skewed. So let's redraw that head on so that we can actually do something with it and solve some of these things. This one, I'm going to pick this one versus the other one just because there's more pieces to it, and it kind of re-emphasizes why you might want to use method of sections instead of method of joints. One thing about that, on the exams, homework, quizzes, I don't specify that you use one or the other. I just give you a problem, and it's up to you to decide if you want to use method of joints or method of sections. All right, so let's make this thing, let's make all those bottom pieces maybe 3 squares, like that. 3, how many are there? 1, 2, 3, 4, 5, there's 6 of them. So there's 2, 3, 4, 5, 6. Okay. And then let's make the height of this thing maybe, I don't know, compared to those, it looks like 2 of those, so maybe 6 tall. So in every one of these middle areas, there's a 6 foot or 6 block. 1, 2, 3, 4, 5, 6. Is that 6? So there's one here, one here, one here, and one here. That didn't look, yeah, that's right. And then we connect the ends together with 2 separate pieces. So there, and then there's a little piece there. There, there, little piece there. There's pieces across the top. And then we have a bunch of diagonal pieces. So we've got a solid piece from there to there, and then up, down, just kind of zigzagging across there. So there's our truss, and then each one of these is a joint. I'll just draw a circle for the joints. So this would be our diagram of what we would analyze if we were trying to analyze that truss on the right using method of joints or method of sections. It looks like it's supported at the very ends, like there's a support column there and a support column there. So let's remember, we are going to treat one of these as a roller. We can't even see close enough on those to tell which one's allowed to slide or where the ability for this bridge to expand is. If I lock everything down and then it heats up, like it's outside obviously, and it gets to 110 degrees or whatever, and it heats up, that metal wants to expand, and if I've locked it down, it has nowhere to go, and so it'll start buckling. Or if it gets really cold and it wants to contract, and I've locked the 2 ends down, it has nowhere to go, and it'll try to pull the supports down. So I have to have some way for this thing to expand and contract. Not quite the same, but if you've ever driven over a bridge and you've heard that periodic thumping sound, those are expansion joints. They're like little rubbery sections between the roadbed. So they put down some distance of roadbed and then a little rubbery section, then some more roadbed and another little rubbery section, so that each one of those sections can, not the same sections that we're talking about truss sections here, but each one of those sections of pavement can kind of expand and contract without having to push on its neighbor. So we have to take that into account. All of that to say, we're going to model the supports, one of them being a pin and one of them being a roller. In our case, we don't know, so we're just going to not randomly, but I'm just going to say that this one's the pin and this one's a roller. So that's what I'm using to show a roller, and this time this is what I'm using to show a pin. Okay. Our picture doesn't have any other than the weight of the bridge, which a lot of times you ignore the weight of the bridge, sometimes you include it. For simplicity, we're going to ignore its own weight. We're only going to assume there's some kind of car driving over this thing. You can kind of see that there is a roadbed in there, and that roadbed is continuous, or maybe it has the expansion joints in it, but it's not really part of the truss, but the truss is holding up this roadbed, and it's supported. We're going to show that the roadbed is supported on these lower joints. So I think what I'll do is I will just, since there's no cars on there, I'm just going to evenly distribute what I think the roadbed might weigh. But remember, I can't put forces on these pieces. That was one of my rules. If I want to analyze it as a truss, I can only put external forces on the joints. So that's the road bed. I've got 5 of them. I'm going to say that, I don't know, what's a good weight for a road bed? Let's make it an easy number and say it's 50,000 pounds, which I don't know, that might be underestimating it, but let's say it's 50,000 pounds. We've got 5 of these, so each one is 10. Remember, we use those kips sometimes when we have big numbers. So a kip, just so you remember, equals 1,000 pounds. So if I needed to distribute some force, but I can't put it on the members, you know, I couldn't do, we haven't talked about distributed loads, but I couldn't like put a distributed load on the member itself because then I can't analyze it as a truss. Then I can just assume whatever distribution I want. In this case, I said that each one of these evenly supports the weight. The pin and roller, they'll have their own reactions. So, and I just divided it evenly. But maybe if I had reason, I could divide it some other way. So that's kind of how I would take care of the road bed. And we could have other forces on this. Maybe there is a car driving across it. We could put a car somewhere. We would just have to divide its weight across whatever joints we thought it was closest to. But let's just do this. This looks fine. So let's label our joints so that we can talk about them. We're starting the left with A and go around clockwise. Okay, there's our joints labeled. We have our grid in the background we can use as dimensions, but let's go ahead, and this doesn't look like well, there's a tree. There's a tree under there, so it is a pretty big bridge, big enough for 2 cars to go through it side by side. So that's 2 car lanes, or what? They're like, I don't know, what are they, 18 feet wide? I don't know how long ago. Let's just say that this whole thing is 40 foot wide. Let's make each of these 30 feet. So each block will be 10 feet basically. I don't know if that's realistic or not, but that's what we're going to use. It's not completely unrealistic, so that'll work. And that would make our height 60 feet. I'll have to kind of work around our label there. And then we have that B and H that look like they're 25 feet tall. If we need that dimension too, it's really, you know, messed up there where I've put it, but I'm thinking we are not going to need that for what we're going to do, but there it is. And this would be 20 feet. Okay, so that's not our free body diagram because we still are showing the pin and the roller. So this is more like the diagram of the situation. Once we want to draw the free body diagram, we kind of need to redraw the whole thing again. I'm not going to make you do that. I'm not going to do that. I'm going to cheat because I have a digital thing here. So we're going to copy it. And we're going to paste it. We're going to line it back up with the grid so that it's kind of in the same spot that it was. And then I'm going to erase the pin and roller. So that pin would have 2 reactions, AY and AX. I can already tell that AX is going to be 0 because it's the only arrow that's going to be in the X direction, so it has to be 0, the way I've drawn everything here. And we'll erase the roller. We can fix our dimensions here. Well, actually, I need some room there. I'm going to put, this was a roller. I had drawn it rolling on a horizontal surface, so that means the reaction is vertical, and there's only one reaction. So that'll be I in the Y direction. Now we have a free body diagram. We could, if we wanted to, just to make sure everybody understood that X is horizontal, positive to the right, and Y is vertical, positive, up. Just so that everybody's on the same page, although that's kind of understood. All right, no questions in the chat, so we're good. We're up to 8 votes, all good, all okay. All right, now we haven't actually said what we want to solve for. So let's say that our problem statement is we're given all of this. Actually, we were probably given this picture here, and now we have kind of started working on our free body diagram. And we want to find the force in, let's say, EK. Anytime I pause, it wants to straighten out the line. Force in EK and EF. So those would be the ones that we want to find. So we could do that with method of joints. We could find our external reactions, start at I or A, and work our way, maybe start at L, and work our way towards E, K, and EF. So we could do that. So these are the two. We want to know that one, and we want to know that one. So since they're in the center of the truss, that kind of hints to me that I probably want to use method of sections. And there's a decent, cut I can make like that, where it cuts the truss into 2 completely separate sections, and it cuts through the 2 I want to solve for, EK and EF, and it doesn't cut through any more than 3 members. So that looks like it'll work. Before I do the cut, though, I need to find some of my external reactions. So method of joints, last time, we had to find these external reactions first because we wanted to start at joint A, and so we needed to know at least the reaction at A. It is possible with method of sections that you can cut off a section where it doesn't have a reaction at all, and you don't need to solve for any. In this case, if I use the left-hand section, then if that's the one I'm going to use and I draw, then I need to know what AY is going to be, because that's part of the left-hand section. If I look at the right-hand section, which would be just as valid to use, I would need to know IY. So I need to know one of those, if not both. We'll go ahead and solve for both just to have the practice of doing it, but we need at least one. But sometimes you don't need either of them, depending on how you can make the section. All right. Let's see. Next, we need to solve for AY and IY. So we're going to do that before we cut the truss into sections. So remember, you have 3 equations, 3 equilibrium equations for static equilibrium. Actually, you have 4. I just keep throwing out the Z because we are only doing 2D stuff. But you actually have 4. You have X, Y, Z, and moments. So let's just, for the sake of it, let's write summation of forces. We kind of already wrote the X one when we wrote AX equals 0. We just did it in our minds that, well, it's the only arrow I've drawn in the X direction, so it has to be 0. So let's just do Y. So we have AY, and then we have, that's in the positive Y direction, minus, there are 5 of the same thing. They're all 10 kips. So I could write out 10 minus 10 minus 10 minus 10. You could do that. I just did 5 times 10. Plus IY equals 0. So all that tells me is AY plus IY equals 50 kips. That's all it tells me. And I can't solve for that. Usually this is what happens. And so usually when you're solving for external reactions for a truss or some other object that we haven't gotten to yet, then usually you want to do a summation of moments first. And I said earlier, last time when we were talking about moments, that with trusses and other things, but trusses in particular, when you're doing the external reactions, it's usually best to do the summation of moments about the pin. The pin was at A, so summation of moments about A. We will say clockwise moments are positive. You get to choose that though. Those are going to equal 0. And that equation says that whatever forces are on this truss, the moments that they create about point A add to 0. Because I know that the truss is not rotating about point A. And I could have picked any point. It doesn't even have to be one of these points that I've drawn. It can just be any point that I know the truss isn't rotating around. So let's write this equation. So I've got AY, the very first, well, AX I've already decided is 0. AY is the first one. Its line of action actually goes on top of A. So it does not create a moment about A. That's the idea of trying to open a door by pushing on the door hinge. So the door doesn't rotate. But so I go to the 10K, the first 10K. 10 kips, that's a vertical force. So the distance between point A and that force, I want the horizontal distance between it, which is 30 feet. And I need to assign it positive or negative. I said that clockwise was positive. If I isolate just this force, think of there's no other forces on there, and I'm imagining this truss rotating about pin A, then that force about pin A, or point A, would make the truss go clockwise. It would spin around clockwise. So I give it a plus sign. Well, I guess I can write a plus sign. It doesn't matter. But then I do the next one. 10 kips times, so I'm looking at this one now. That one is 60 feet from point A. It would also go clockwise, so that's a positive number. And they're all going to be positive. All the 10 kips are. So 10 kips times 90 feet plus 10 kips times 120 feet plus 10 kips times 150 feet. And then I get to IY. That arrow, now I just drew the arrow going up. I don't actually know that it's going up. I just drew it in the positive Y direction. But so that would give it, if I was only looking at IY and pin A, then that truss would go around counterclockwise around A. So it needs a negative sign. So minus, I don't know the value of IY, but I know that it's 180 feet from the pin. Actually, I didn't do the others that way, did I? Did that. There we go. All of those multiplications and additions, that has to add to 0 for the truss to actually not be rotating about point A. Those are all the external forces taken into account. All the forces that could possibly make the truss rotate about any point, and we're looking at A. So if they don't add to 0, then that means that the truss is rotating about point A, and I know it's not. So, did I lose my calculator again? I have my phone, and I had my calculator, and now I don't see it. Let me look a second here. Oh, there it is. Okay. Let's see. Let's see. 10 times 30 plus 10 times 60 plus 10 times 90 plus 10 times 120 plus 10 times 150 equals 4,500 foot-pounds. So 4,500 kip feet, right? My units on those are kips. So kip feet equals, and then the IY, I'm going to move it to the other side of the equal sign. So equals IY times 180 feet. So if I divide my 4,500 divided by 180, I get 25. 25 kips. Now, some of you are probably saying, well, that's obvious because I've got 50 kips total and they're all evenly spread out and my truss is symmetric. I could just say that, well, 25 is reacted at one end and the other 25 is reacted at the other end. So we could have just done that. But it won't always be everything symmetric and all the loads are even and everything like that. So we worked out the equation. Then I could take that IY, plug it into my Y equation, and I could indeed confirm that AY is also 25 kips. All right, however you do it, we have our external reactions now. Okay, so that means we can start using our method of sections or method of joints if we wanted to do that. We're doing method of sections. I have decided, since we've been talking, that the right-hand side of this truss looks like it's easier to draw because there's less pieces to draw. So that's the one I'm going to draw the free body diagram of. So I'm going to, let's see, I'm going to copy this. Again, on regular paper, you have to, do this the hard way. But since we at least have this digital thing, we can do it the easy way. Now, I have actually cut this off. I'm following my kind of green cut line there, so that doesn't exist in my free body diagram. The points do, though, so they're still there. So if I need them, that was E and that was L. So they're still out there. And I cut through EF, so I'm going to say that, well, I have to replace that with a force in EF, so that'll be the force in EF. There's the force in EK, and there's the force in KL. You don't have to, but normally you alphabetize the letters when you have a truss member, FG instead of GF, stuff like that. So what we have done, and IY is not a variable anymore. IY is actually 25 kips. So what we've done is we have drawn the free body diagram for the right-hand section of our truss. We cut through three members, EF, EK, and KL. And we have accounted for the external reaction. You can't cut it and then solve the external reaction. You have to, if you need the external reactions, you have to solve them before cutting it apart. So we've got all that. I guess I can restate that Y is positive when it goes up, just in case there's any confusion. And we've got a decent free body diagram. So once you get to this point, you have three equations. So X and Y, just like a concurrent force system, a 2D concurrent force system, and you can write a moment equation about some point. So it usually, when you're doing method of sections, you're probably doing method of sections because you only want to know one or two things, and you don't want to have to solve for everything. In our case, we want to know two things. We want to know the force in EF, and we want to know the force in EK. So it usually pays off to spend a little bit of time, maybe 30 seconds thinking about, well, which one of these or which combination of these equations should I use to solve for what I want to know. So thinking about the x equation. If I were to write the x equation, all it would tell me is that, hey, there's a EF has an x component, KL has an x component, and EK has an x component, and somehow they add together to 0. So it wouldn't really tell me anything useful. So that's not very good. The y equation, now that one, I've got three known values, 10, 10, and 25, that are in the y direction. And I've got one unknown, the y component of EK. So that one will tell me one of the things I want to know by writing one equation. So let's write that. So summation of forces, the y direction equals 0. I have drawn, you can see over here, I drew that y is positive when it goes up. So I've got minus 10. Oops, let's write it in black. Minus 10 kips. That's that guy. I've got minus 10 kips. That is that one. I've got plus 25 kips. That's that one. And then I've got the y component only of this EK. So plus FEK times however you want to do this. So let's see. I have got, let's just do the, last time we did rise over run. This time let's do the angle. So let's say that we want to know, we'll do it in blue. We want to know that angle theta. So let's pull that over here. There's theta. And what do we know? We know that this distance is 30 feet and this distance is 60 feet. So that those are the hypotenuse and the adjacent side. So that's cosine, right? So cosine equals adjacent side over the hypotenuse. So cosine of theta equals the adjacent side 30 feet over the hypotenuse 60 feet. And we can, oh no, the 60 feet is actually the, whoops, that's the opposite side. Don't do what I do there. So that's actually a tangent. We got to do that all over. Erase all that. All right, I put the 60 feet labeled over here, and I kind of showed it connected to that, but that's actually, that's actually this height, not the diagonal piece. Tangent of theta equals opposite over adjacent. So theta, or tangent of theta, equals the opposite side is 60 feet over the adjacent side is 30 feet. Therefore, theta is equal to something. Let's see. How do I do inverse tangent? Inverse tangent. Nope. That's not it. Inverse tangent of 60 over 30 is 63.43 degrees. Okay. So that's our angle theta. So what we can do is, the way I've measured this theta, I would need to do FEK, the force in member EK, times the sine of 63.43 degrees. That would give me only the y component of it. Or you could do what we did last time, where we had, where was one of it? Right here, where we did the rise over run and use the definitions themselves. So whichever you want to do. Sometimes you'll have mixtures, like on a test problem, I might give you the angle. I might give you the dimensions, might give you some of both. So I would be familiar with either one. I'd have my preference, but and my preference is usually this method, but be at least okay doing either one of these methods. All right, so let's do our math here. So we've got -10, -20, plus 25, so that's a 5 kips. And then plus FEK, whoops, not X, K times sine of 63.43 degrees equals 0. So we can solve for FEK. I keep writing an X. FEK equals, we got to move that 5 to the other side of the equal so it becomes negative. -5 kips divided by sine 63.43 degrees equals, let's see, negative 5,000. Well, let's do 5. 5 divided by sine of 63.43. I just realized I don't know if this, I think this is in degree mode. 5.59. I think I see a D on the, and I think that means degrees. So hopefully, let's do one I know so that, yes, sine of 90 is 1, so it is in degree mode. All right. All right, so we got to deal with this negative sign. So the negative does not necessarily mean tension or compression. It means that I drew the arrow the wrong way. And so we had to look back at our diagram over here. And I drew FEK kind of up and to the left. And apparently it should be going down and to the right. And if it did that, it would be pointing towards the member EK, which means it's a compressive force. So the right way to write this would be FEK equals 5.59, those were kips. And then I'd write something like that for signifying that it's in compression. Because these things do behave differently in tension and compression. If you have a long, like a ruler, and you pull on it, it doesn't really do anything. But if you push on that, maybe a yardstick or a little plastic ruler, you push on it in compression, then it buckles really easily. And so you have to be aware, are these tension forces or are these compressive forces? Because it's going to make your truss behave differently. So now I've got a new thing though. I could go back to the forces in the X direction, but I'd still have two unknowns. I'd still have those two unknowns in one equation, so that wouldn't work. I've already written the Y equation, so that leaves me with the moment equation. So when you're dealing with the moment equation, the best way to approach it is to, normally if you're doing method of sections, you have three unknowns. Actually, we only have two unknowns now because I solved for one of them, but there's three unknowns, and you want to solve for one of those. So if you can find what the other two have in common, like what point they have in common, some moments about that point, then you'll eliminate them from the moment equation and you'll solve for the one that you want. So I've already solved for EK. My problem statement said to solve for EF and EK. So to solve for EF, if I can eliminate EK and KL, the other two unknown things, then I could just write one equation and solve for the force in EF like I wanted to. So it's particularly easy with trusses because you label the joints, and I don't want to solve for EK or KL. They both have K in their name. So if I sum moments about K, neither one of those will be in the equation. And this 10 kips. So this, and this will not be in an equation for moments about K, because their line of action passes directly through K. And that's the open the door with pushing on the door hinge problem where it doesn't do anything. So that's what I'm going to do. I'm going to sum moments about point K in order to solve for EF. Now, it doesn't always work. It depends on how the truss is arranged and all, but in this case, it will work. So, summation of moments about point K equals 0. I'm just going to stick with my clockwise positive moments because that seems to work for me. You can do counterclockwise positive if you want to. And let's just start with this. We've already eliminated, this, and this. We don't even need those in this equation. So let's start with this 10K. So it's going clockwise, and it has a 30-foot moment arm between the 10 kip line of action and point K. So 10 times 30 is my problem. 10 kips times 30 feet. Okay, and that takes care of that 10 kip. Let's do the 25 kip. So it's going counterclockwise, and it has a 60-foot moment arm. That looks like I wrote 30 degrees there. I meant 30 feet. So minus, because it's going counterclockwise, 25 kips times 60-foot moment arm. The only other force is EF. The way I drew it, again, I don't know which way it's actually going, but the way I drew it is counterclockwise, and it also has a 60-foot moment arm from its horizontal line of action down to point K. So minus force in EF times 60 feet. Those all have to add to 0. So let's just multiply and add and all that kind of stuff. So I've got 10 times 30. So that's a positive 300 kip feet. Minus 25 times 60 is 1500 kip feet. Minus FEF, force in EF. Sometimes people use a T. You'll notice I have been, when I don't know a member, actually whenever I draw a member force at all for the first time, I draw them in tension, pointing away from the member. I did the same thing over here, tension, tension. So sometimes instead of writing FEF, people will write TEF for tension in EF, and then that kind of even further solidifies that if you get a negative number, it's in compression because the tension is negative, which would be compression, because tension is a positive force. So you might see some TEFs and TABs and that kind of stuff also. So FEF times 60 feet, I need to equal 0. I need to isolate the FEF, so I get, I'm going to move FEF to the other side of the equal sign, so it becomes positive. FEF equals 300 kip feet minus 1500 kip feet divided by 60 feet. So it looks like it is going to be negative. So 300 minus 1500 divided by 60 is 20. Negative 20. So therefore, the force in EF is equal to negative 20 kips. I go look at my arrow, and yes, I drew it in tension, pointing away from the member EF, little fragment there that I drew. So it's pointing away from it, showing its intention. But when I calculated, it's negative, so it's actually a compressive force. And so our final answers would be here. and here. Okay. Let us mention, all right, so I assume, I don't see any questions, so I assume everybody's okay with that. If we wanted to solve for KL, now we could go back to our X equation. We know the other two. Or we could write a moment equation about E and solve for KL. That was not part of our problem statement, so we won't actually do that. But that would be two different ways to solve for KL if we wanted to know it. All right, one last, not necessarily method of sections, but truss issue is we can see it in this truss. So why don't we get this picture and copy it? Okay. All right, so there is such a thing as a zero force member. So we can see that one easy one to see is right here at D. So we don't need to solve anything, but let's draw the free body diagram or a joint equation at D and see what happens. So I would have, this, and this, and I would have some kind of, that would be the force in DE. There's the force in CD. And here is the force in DM. Okay, that's fine. Let's write our summation of forces in the X direction for this free body diagram. And that would say that, okay, well, FCD minus, or well, actually FDE is going in the positive X direction, minus FCD going in the negative X direction equals 0. DM is vertical, so it doesn't have an X component. So that's fine. It just says that DE and CD equal each other. But what happens when we write this equation? We get FDM negative because it's going down, so minus FDM, but I don't have anything to add to it, so it just equals 0. So there are, there are 0 force members in trusses. Can be. So this is one example of a 0 force member. Now, it doesn't mean that this member is not important. It just means that in this load scenario that technically there's no force, this member isn't doing anything. But if I change up the load scenario a little bit, like maybe I add a force on top here for some reason, I want to take into account the weight of the top of the bridge or something, then now I do have another force I can put in my Y equation. So it doesn't mean that it's useless. It just means that there might be situations where some of the members are technically 0 force values in that configuration. Now you can solve for them this way, where you draw the free body diagram and you calculate everything and it just solves for 0. But it'll be a little better if you can look at the truss and say, oh, well, those are 0 force members in this configuration. In this truss, I see 1, 2, 3, 4. Yeah, I see 4 0 force members in this truss just by looking at it. So here are some rules to find 0 force members without having to go write the equations. Okay, so you've got, first, look for a joint with 3 members. So we've got B has 3, D has 3, we already found a zero force member there, F has 3, H has 3, L has 3, and that's it. So those are our 5 candidates so far. 2 of these members need to be collinear. That means they share the same line of action. Okay, so here AB and BC are collinear. CD, whoa, what am I doing? CD and DE are collinear. EF and FG are collinear. GH and HI are collinear. So, oh, and KL and LM are collinear. So all of these actually still qualify. If they had been a joint where there weren't 2 of the members collinear, then that would throw them out of our little process here. But all of ours had at least 2 collinear members. Now we need no external force at this joint. And I'm going to put like directly over here in parentheses. So B, yep, no external force there. D, no external force there. F, no external force there. H, no external force there. But L does have that 10 kips applied directly at L. Now you might look at D, and there is 10 kips like below it, but that 10 kips is applied at M, not at D. Even though it's in the same line, it's not applied at D, it's applied at M. So we lost L here. L is not a joint that has zero force members in it. So if all of these 3 things were true, the third member, so the non-collinear member, is a zero force member. So BN, oh, let's see, I'd like to erase with a small eraser. There you go. BN is a zero force member. DM, the one we actually saw for earlier, that's a zero force member. FK, zero force member. And HJ, zero force member. So I'm just kind of drawing them as dotted lines. They're still part of the truss, and they still might have a purpose, but they carry zero force in this exact loading configuration. Now, if things start to change, if this truss, maybe the truss starts to bend a little bit. So go back to this, this setup here. If the truss starts to bend and deflect, then I'm going to exaggerate it, but it might look like this. Now when I write summation of forces in the y direction equals 0, there are, FDM is greater than 0. I don't know what it is, but it's not 0 anymore because I've got a y component here and I've got a y component over here. And so FDM, this one, has some value now. So it only applies when the truss is, in its drawn state here. If things start moving around, then it does have a value, and it will support a load. It's not like it never supports a load. So the other thing you can do is, let me move these down a little bit. I need to write one more line. So once you find a zero force member, you have to go back and check again. Now this truss, well, so for instance, we found BN is a zero force member. So now on the second pass, N qualifies, at least for step one. Look for a joint with 3 members. It has collinear and collinear, but it has an external force. So CN is not a zero force member. But it could be. Let's draw a new truss. Like this. We'll put a roller here, pin here, and then let's put, it's holding up some kind of sign. So there's our new truss. A, B, C, D, E, F, G, and A again. Okay, so our first pass, we have, there's 3 members. Oh, you know what? Let's actually take this force off. To prove this point, let's take that force off. So otherwise it won't do anything. So we've got our 3 members here. At F, 2 of them are collinear. There is no, now that I erased it, there's no external force at F. So DE, or DF rather, is a zero force member. And now when I go and look, oh, now D has 3 members. 2 of them are collinear. No external force at D. So DG is a zero force member. Oh, now G has 3 members. 2 are collinear, AG and FG. No external force at G. So CG is a zero force member. C has 3 members. 2 of them, BC and CD, are collinear. No external force at C. AC is a zero force member. So if I wanted to analyze this truss in this configuration, it's really just this. Well, kind of missed there. That's it. Like, none of that stuff on the inside in this configuration would have any value if I calculated it. It would be 0. They'd all be 0. And I'd only have 3 pieces that actually had force in them. So finding zero force members can definitely speed up the ability to solve trusses, because you suddenly realize, in this case, I've found 4 pieces that are all 0. Let's do one other, and then we'll call it a day. So same truss, but different loading. Okay, so this loading. Now this one, there are no joints that have 3. Well, actually there is. That joint has 3 members. 2 of them are collinear, but there is an external force applied there, so that third member is not a zero force member. But there are still 2 zero force members in this truss. And these 2 have to be zero force members because there's no actual force out there. So the fact that they're just kind of going to some point with no force at that point, they would have to be zero force members. You couldn't have this free body diagram and solve these 2 equations with any numbers other than 0. Like, because the horizontal one has no y component, then when I write my y equation, the one that's at an angle says that, oh, well, that one's a 0 value. But then once it's a 0 value, it has no x component. And so the summation of forces in x says that, well, the one that's horizontal has to also be 0. So anytime you have 2 members that come to a point and there's no force at that point, then both of those are zero force members. So only if there's 2, though. If there's more than 2, then you might be able to work it out. But if there's 2 that come to a point and with no force at the point, those both are zero force members. All right. I think that is enough for today. Homework 8 just opened. So that's over here. Homework 8 should be open in web work. Web work is starting to close. Some, I think 4, 5, and 6, 7, 8 are open. Although it look like 8. Did it not open 8? I might have to open 8, or maybe it's not updated. Let me see. Oh, of course. So it looks like I need to update 8. So something's weird with 8. 8 is about to be open. Also, this SA01, I was talking about challenging problems. I think they've been rolled into this SA01, 2, 3. But if you started it earlier, it had a time limit on it, like a quiz or something. I have removed the time limit, so it's just open. I'm going to use those as the challenging problems, since I don't seem to have the actual challenging problems anymore. But I think they've been rolled into these. But if you tried it before, it had a time limit and it might have closed on you. It should be just open like a regular homework set now. So that should take care of all of trusses. We'll keep including trusses in the things that we do. And we'll, they'll be part of other topics. But unless I have specific questions, or you can ask to see a particular problem solved. Sometimes I can work a web work problem, or just one that you found on the stream. But for the most part, we're going to be done with trusses, and we're going to move on to this idea of centroids. We'll do that on Wednesday. Should be a live stream at noon. All right, I will see y'all then.